Imagine yourself riding a wave on the ocean. You effortlessly glide along, guided by the powerful force beneath you. The wave dictates your path, its hidden currents determining your every move. This, in essence, is the picture painted by the pilot wave theory, a fascinating yet controversial interpretation of the bizarre world of quantum mechanics. Instead of particles being tossed around by chance, as traditional quantum mechanics suggests, the pilot wave theory proposes a more elegant deterministic reality. Just like the surfer guided by the wave, particles in this view are steered by a hidden pilot wave, their trajectory is predetermined from the start. This intriguing alternative offers a fresh perspective on the fundamental nature of reality, and it all begins with understanding the puzzling world of quantum mechanics itself. Quantum mechanics, the theory governing the behavior of the universe at its smallest scales, is renowned for its strangeness. It challenges our classical understanding of reality and forces us to rethink the very nature of existence. It's a realm where particles can exist in multiple states at once, a concept known as superposition. Imagine a world where a single particle can be in two places at the same time, or even spin in opposite directions simultaneously. This is like saying you can be in New York and London simultaneously until someone observes you, at which point you collapse into one definite location. This phenomenon is not just theoretical, it has been demonstrated in numerous experiments. This inherent uncertainty is captured by the wave function, a mathematical entity describing the probability of finding a particle in a particular state. The wave function is a fundamental concept in quantum mechanics, representing all possible states of a system. When we measure a particle's position, for instance, the wave function is said to collapse, forcing the particle to choose a definite location. This act of measurement is crucial as it determines the outcome of the particle's state. This collapse is a source of much debate and philosophical head-scratching. Scientists and philosophers alike ponder the implications of this phenomenon, questioning the nature of reality and the role of the observer. Does the particle truly exist in all those states at once? Or is it our observation that brings it into a single state? These questions challenge our understanding of the universe. And what role does the observer play in collapsing the wave function? Is the observer an integral part of the quantum system, or merely an external influence? These are just a few of the questions that make quantum mechanics so perplexing yet captivating. The mysteries of the quantum world continue to inspire and challenge scientists, pushing the boundaries of our knowledge and understanding. Enter the pilot wave theory, also known as de Broglie-Bohm theory, a compelling alternative to the traditional interpretation of quantum mechanics. Developed in the 1920s by Louis de Broglie, this theory was a groundbreaking attempt to understand the quantum realm. Later, it was refined by the brilliant physicist David Bohm, who sought to bring clarity and determinism to the seemingly chaotic quantum world. The central idea is simple yet profound. Every particle in the universe is guided by an invisible pilot wave which acts like a hidden hand steering the particle. This wave, described by a precise mathematical equation, dictates the particle's path, just as the ocean wave guides the surfer. Imagine a surfer riding a wave. The wave's shape and motion determine the surfer's trajectory. In this view, the particle always has a definite position and momentum, even though we can't know both with perfect accuracy at the same time. This is due to the inherent limitations described by Heisenberg's uncertainty principle. This stands in stark contrast to traditional quantum mechanics, where particles exist in a haze of probability until measured. In the traditional view, particles are like ghosts, existing in multiple states at once until observed. The pilot wave theory offers a more intuitive and deterministic perspective, suggesting that the universe is not as random as it seems. Perhaps the most famous illustration of the differences between these interpretations is the double-slit experiment. This experiment has fascinated scientists and lay people alike for decades, as it reveals the mysterious and counterintuitive nature of quantum mechanics. In this experiment, particles such as electrons or photons are fired at a barrier with two slits, and their pattern on a screen behind the barrier is observed. The results of this simple setup have profound implications for our understanding of the universe. Intriguingly, even when particles are sent one at a time, they still create an interference pattern on the screen as if they were waves interfering with themselves. This suggests that each particle somehow travels through both slits simultaneously, a concept that defies our everyday experiences. Traditional quantum mechanics explains this by saying the particle passes through both slits simultaneously as a wave of possibilities, interfering with itself before collapsing into a definite point on the screen. This wave of possibilities is known as the wave function, which describes all the potential states a particle can be in. The pilot wave theory, however, offers a different explanation. According to this theory, the particle always goes through one slit, but its trajectory is guided by the pilot wave, which itself passes through both slits and creates the interference pattern. This pilot wave acts like a hidden hand, directing the particle's path. Both interpretations account for the observed results, but they paint drastically different pictures of reality. Traditional quantum mechanics suggests a world of probabilities and uncertainties, while the pilot wave theory implies a more deterministic universe, where particles have definite paths influenced by unseen waves. The debate between these interpretations continues to be a central topic in the quest to understand the true nature of quantum phenomena. The implications of the pilot wave theory are far-reaching. It suggests that the universe is not governed by chance, but rather by a deterministic set of laws. Every event, from the smallest particle interaction to the formation of galaxies, is predetermined from the beginning of time by the precise initial state of the universe and the guidance of the pilot wave. This deterministic worldview has profound philosophical implications, challenging our notions of free will and the nature of reality itself. If everything is predetermined, then are we merely actors playing out a pre-written script? Or does the pilot wave theory simply reveal a deeper level of order and predictability beneath the apparent randomness of the quantum world? Despite its elegance and explanatory power, the pilot wave theory remains outside the mainstream of scientific thought. This is partly due to historical reasons, and partly due to the theory's inability to fully address certain aspects of quantum mechanics, such as the behavior of particles in high-energy physics experiments. Moreover, the pilot wave theory introduces the concept of a non-local universe where events in one location can instantaneously affect events in distant locations, seemingly violating the speed of light. This non-locality has been a source of much debate and skepticism within the scientific community. Despite these challenges, the pilot wave theory has recently experienced a resurgence of interest. New experiments and technological advancements have allowed scientists to test some of the theory's predictions with increasing precision. For example, experiments using droplets bouncing on a vibrating fluid bath have provided compelling visual evidence for the existence of pilot waves, albeit in a macroscopic system. Furthermore, the pilot wave theory has found applications in diverse fields, including condensed matter physics and quantum computing. These developments suggest that the theory, while still controversial, holds significant potential for advancing our understanding of the quantum world. The pilot wave theory, like the vast ocean, still holds many uncharted depths and unanswered questions. What is the nature of the pilot wave itself, and how does it interact with particles? Can the theory be reconciled with Einstein's theory of relativity, which forbids faster-than-light communication? And perhaps most importantly, can the pilot wave theory provide a more complete and satisfying description of reality than traditional quantum mechanics? These questions continue to intrigue and inspire physicists and philosophers alike, driving further research and exploration into the foundations of our universe. The answers, if found, have the potential to revolutionize our understanding of reality and our place within it. The pilot wave theory offers a captivating vision of the universe, a cosmic dance choreographed by the elegant movements of hidden waves. It challenges us to look beyond the apparent randomness of the quantum world and seek a deeper level of order and determinism. Whether or not the pilot wave theory ultimately proves to be the correct description of reality, it serves as a powerful reminder that our understanding of the universe is constantly evolving. As we continue to explore the depths of the quantum sea, we may find that the most profound discoveries lie not in confirming our existing beliefs, but in daring to imagine new and unexpected possibilities.